Hello everyone and welcome to the video on section 3.5 limits at infinity. Our objectives for this particular video are number 1, determine limits at infinity, finite limits at infinity. Number 2, determine the horizontal asymptotes, if any, of the graph of a function. And the third one, determine infinite limits at infinity. Let's start out by just kind of getting an idea what we mean by a limit as we go off to a limit at infinity. So what's happening here, we have this particular function here. F of x is 3x squared over x squared plus 1. And if you plug in, I made a table of values here, so when you plug 0 in, you get 0. But you'll notice the symmetric relationship that exists here. That when you put in 1, you're going to get 1.5. When you put in 10, you get 2.97. When you put in 100, you get 2.999, and then the next one would be 7. And really what's happening in this case is that as you put in larger and larger values of x, the function values are moving closer and closer to 3. So in this case, as x goes towards infinity, my function values are going towards 3. And so what I would say in this case is that the limit as x approaches infinity of f of x would be equal to 3. Now if we take a look at what happens, the behavior of what that happens as you go towards negative infinity, and you're going to notice the same type of situation. In this case, when you put in negative 1, you're going to get 1.5. Negative 10, you get 2.97, just like we did over here. Negative 100, you get 2.9997. And again, as our x values go off towards negative infinity, in other words, get to be a large negative number, my function values are still approaching the same value, happen to be approaching 3. So I would say that the limit as x approaches negative infinity of f of x is equal to 3. So really what you're looking at, when we talk about the limits as x goes off towards positive or negative infinity, what you're really looking at is what is happening to the function's behavior, what's happening with the function's values as x grows without bound in either the positive or negative direction. And if that function value is approaching a specific number, then like we have in this example here, then that value that it approaches is going to be the limit as you are approaching positive or negative infinity. Now we're going to talk about the formal definition. I'm not going to really go into the nuts and bolts of the formal definition, but kind of give you just an overview. The idea behind the definition of a limit as x goes to infinity is that if you go through and you move or move a small amount off of the limit. So in this case, we're looking at this thing, the limit of this function as x goes towards positive infinity is 3. The limit as x goes towards negative infinity is negative 3. You can see the graph here going down and keeps getting closer and closer there and comes closer and closer here. Now what happens when we're talking about these is that we can move, for like looking at the limit as x with 3, we can move just a little bit off of 3. And that little bit, they use the Greek letter epsilon. And what happens is that we can go across, hit the curve, and come down. And we can call that number m. And what this says is that no matter how small you make this epsilon, that distance from 3 to here, no matter how small you make it, you're always going to be able to go across, hit the curve, and come down and find another m, so that if you are closer to 3, that the value that it's going to hit is going to be bigger than m. Okay, and that same thing is kind of true when you're dealing with the negative infinity, when you're going off towards negative infinity as well. So we're going to take this, and we're going to take our epsilon, we'll just go right there. And again, the idea is that we can go across here, hit the curve, and we can get some number here, call it M2, and no matter what, if we go into get something closer to -3 than we are right there, then we're going to come across and we're going to hit that value. It's going to hit that value over much farther down from where we're at with M2. That's really what you're looking at with this, like kind of the formal definition that they have for this limit. Now, what this all comes down to is really looking at horizontal asymptotes. If you look at this, the definition of a horizontal asymptote is the line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. In other words, when you're finding the limit as x goes to positive or negative infinity, what you're really doing is you're finding the horizontal asymptote for that particular function, if one exists. If the limit does not exist, then there is no horizontal asymptote. If the limit does exist, then you do have a horizontal asymptote. So now that we know that the limit as x approaches infinity of a function f of x really represents the horizontal asymptote. Some functions we are familiar with their horizontal asymptotes, and one of those that we have is the rational function. Rational function is where you have a polynomial over polynomial. So what happens here is if you're looking for the horizontal asymptote, what you're really looking at is the degree of the numerator and denominator. Remember, that's the highest power on the x in the numerator and denominator. And so what we have is this: if the degree of the numerator is less than the degree of the denominator, then the limit of that rational function as x goes to positive or negative infinity is going to be 0. If the degree of the numerator is equal to the degree of the denominator, then the limit is going to be of that rational function as x goes to positive or negative infinity is going to be the ratio of the two leading coefficients. And those are really the coefficients on the highest degree term in the numerator and denominator. And the third one is if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. Let's take a look at a couple of examples. In this first example, we're taking the limit as x approaches infinity of x cubed minus 3x squared plus 1 over x to the fourth minus 2. In this situation right here, the degree of my numerator is 3, because that's the highest exponent, highest power of x we see in the numerator. The degree of the denominator is 4, because that is the highest power of x we see in the denominator. So in this case, all we're going to do is we're going to go through and say, oh, in this case, the degree of the numerator is less than the degree of the denominator. So for this particular problem, this limit is going to equal 0. In the next one, the degree of my numerator is 1. The degree of my denominator is 3. So again, that limit is going to be 0. And in this third one, we have, if you look at that one, the degree of my numerator is 2, because it has the x squared term. The degree of my denominator is also 2, so it's equal. So the limit is just going to be the ratio of their leading coefficients. Now, the leading coefficients are the coefficients on the highest degree term. So in the numerator, my leading coefficient is 3. In the denominator, my leading coefficient is -7. So in this case, that limit is -3/7. In this next one here, we got the limit as x approaches infinity of x over the square root of x squared minus 4. Now this one is not a rational function because it's not you don't have a polynomial in the denominator. So we want to go through and evaluate this limit. And our first instinct on it is to just plug in the infinity. And when I do that, I'm going to get in the top, that is going to be infinity. And in the bottom, I'm going to get infinity, the square root of infinity squared minus 4. Well, that is just going to also be infinity. And this is another indeterminate form. Just like 0 over 0 was indeterminate, We've talked about that one. This is an indeterminate form. And what we have to do is we're going to algebraically try to modify this so that we can find the limit. And the way we're going to do this is, remember that on a fraction, I can multiply or divide the numerator and denominator by the same thing. So what I'm going to do is I'm going to go and divide the numerator and denominator by x. So when I do that, I'm going to get the limit as x goes towards infinity of x divided by x over the square root of x squared minus 4 divided by x. Now notice I put the division by x's in blue to indicate the difference. What you see in black is what we have in the original problem. So all I've done is take what's in the numerator and denominator and divided it by x. Also notice here that this x here is outside of the square root right now. Okay, so that's what you got. That's a very important thing to keep in mind. And what we're going to do is we're going to take this and we're going to modify that. Really what's going to happen is we're going to take this x here and bring it inside the square root, which means that when we pull that inside, it's going to end up being an x squared. So what we're going to have here is this is going to equal the limit as x goes to infinity of x over x over, when I bring the division by x inside the square root, it's going to be the square root of x squared minus 4, and then I'm going to put this one here over x squared. Notice how if I was to break that square root up as a square root of the top over the square root of the bottom, I would get back to what I have over here. So now what this is going to do is that's going to equal, I'm going to put that I'm going to break that up. It's going to equal the limit as x goes towards infinity of x over x over the square root of x squared over x squared minus 4 over x squared. And now when I simplify that, that's just going to be the limit as x goes towards infinity. X over x is going to be 1 over the square root of x squared over x squared is 1 minus 4 over x squared. And now if I take the limit as x goes to infinity here, that numerator is just going to be 1. The denominator is going to be the square root, well, square root of 1, with the 1 there as x goes to infinity, that's going to be 1, but minus 4 over x squared, the limit of that as x goes to infinity. You're going to have 4 over a very, very big number. You take a constant over a very, very big number, that's going towards 0. So that is going to end up being 0. So in this case, that limit is just going to come out to be 1. And that would then be the limit as x goes towards infinity. So with that, this does now conclude this particular video on the limits as x goes towards positive or negative infinity. In class, we'll take a look at a couple other examples. Maybe look at also solving these, finding these limits again and when it's not a rational function. But with that, I hope everything's going well, and I will see you in our next class.